Okay, so continuity. Roughly speaking, a function is continuous on an interval if there are no breaks in the graph. So that means no holes, no jumps, no vertical asymptotes. In other words, if I was to draw the graph of the function, I could do so without ever lifting my pencil. So here's an example of a continuous function. Okay, and I'm just going to draw the function over this interval. And my graph, you can see I'm drawing it without ever lifting my pencil. It's just one continuous curve. The arrow means the graph keeps going. Okay, so that's an example, a simple example of a continuous function. More formally and precisely, we're going to define what it means to be continuous at a specific number. So here's our first definition. A function f is continuous at a number a if the limit as x approaches a of my function, f of x, is equal to f of a. Okay, so let's take a minute and think about what that's saying. The very first thing that must be true for this definition to hold is that the function has to be defined at a. So in other words, a must be in the domain of my function. So I'm just going to write that down as 1. A is in the domain of f. So in other words, f of a is defined. The second thing that must be true is that the limit has to exist at a. So I'm going to call that number 2, and I'm going to say the limit exists. So note that this means that the limit has to be equal to a finite number, like -5 or 7. So if the limit is infinite, like negative infinity, positive infinity, then we would say the limit does not exist. Okay. So now the third thing that has to be true is that these two quantities have to be equal. So whatever the function value is, f of a, it has to be equal to the limit. So I'll call that condition 3. Okay, so let's look at a quick example and see what could possibly go wrong. Okay, so if I look at this example over here, if I was to try to draw this graph, you can see I would have to lift up my pen at 0, at 1, at 2, and at 4. So I can immediately see that my function is discontinuous at x equals 0, discontinuous at x equal 1, discontinuous at x equal 2, and discontinuous at x equal 4. There's no problem at x equal 3. We're allowed to have sharp points or corners or cusps. Okay, so the next question we might want to ask is, so what part of the definition that we have up here fails at these different points of discontinuity? Okay, so let's take a look at what happens at x equals 0. If I look at this, if I look at the graph near x equals 0, what I can see here is that I have an infinite limit, okay? I can also see the function is not defined. So number 1 fails. The f of a is not defined. So let me just write that down. I can also see that the limit does not exist. And the reason it doesn't exist is because it's infinite. Okay? Now if I look at x equal 1, it's pretty clear that the function is not defined. That's what the open circle means. Okay, if I look at x equal 2, now I can see in this case the function is defined. F of 2 is equal to 1. However, if I approach 2 from the left, the limit is 0. If I approach 2 from the right, in this direction, the limit is actually equal to 1. So the left and the right hand limits are not equal, and in this case, we would say the limit does not exist. Okay, if I move on to x equal 4, we can see that what's happening here is, so the function is defined at 4. F of 4 is equal to 2. And the limit also exists, right? As we approach 4 from the left or the right, it's apparent that the limit of the function is 1. The problem is that 1 is not equal to 2. So in this case, the third condition fails. So in this case, the limit as x approaches 4 from either direction is not equal to f of 2, or f of 4. And we have that this value here is equal to 2, and this value is equal to 1. So condition 3 fails. Just as a side note, these different types of discontinuities have names. This is what the first discontinuity that we see over here is what we would call an infinite discontinuity. And that's because we have a vertical asymptote. The discontinuity that we have at 1 and the discontinuity we have at 4, these are called removable discontinuities. And here we have removable discontinuity. And notice that in both of these cases, the limit exists in both of these cases. The problem really only happens at that one point. And so if I just remove that one, point, or I added a point there, or I changed the definition at just that one value, my function could be continuous. So those are removable discontinuities. Over at 2, you'll see that there's a jump in the graph, and this is what we call a jump discontinuity. At x equal 2, over here, my function is actually continuous from the right. And what this means is that the limit as x approaches 2 from the right, and in this case that limit that we can see here is 1, that value is actually equal to f of 1, okay, so, or f of 2, sorry. So these two values are equal, they're both equal to 1, and that's what continuous from the right means. And notice how we don't have continuity from the left or right occurring at 4 or 0 or x equal 1, okay? Because the function has to be defined and the limit from the left or right has to exist. The basic shape that you see when we talk about continuity from the left or continuity from the right, so the basic shape you'll see is, if the function is continuous from the right, you'll have this shape. And if the function is continuous from the left, you'll have this sort of shape. Okay, so if this guy was like a little tadpole and he was swimming from the right, you'd have continuity from the right. And if the little tadpole was swimming from the left, you would have continuity from the left. Okay? Okay, so another question we can ask about this graph is on what intervals is f continuous? Okay, so if I look at the graph, I can see that it's continuous from negative infinity to 0, but not including 0, so I use the parenthesis here. It's also continuous from 0 to 1, but again, not including 0, not including 1. From 1 to 2, on this interval you see right here. From 2 to 4, and since it's continuous from the right at 2, I'm going to actually replace this with the closed interval notation. And also it is continuous from 4 to infinity. So these are the intervals on which my function is continuous, with 2 included because it's continuous from the right, even though the function is actually discontinuous at 2.